Okay, good morning, all of you. Today we are going to discuss the another interesting part of advanced spectroscopic method, deuterium exchange. It is also called as D2O. Deuterium, you know that deuterium is a isotope of hydrogen. As you know that there are three isotopes of hydrogen. One is hydrogen, second one is deuterium, and third one is tritium. Now, what is the impact of that deuterium as far as NMR spectroscopy is concerned? This is very interesting to know you. Now, definitely there will be question on the examination or in the paper that you have to write the answer very well. Deuterium exchange, it is shortly written as a D2O. You know that S2O. Just like H2O, hydrogen is replaced by deuterium. Therefore, it is called as D2O. So, it is a oxide of deuterium that is called as D2O. So, remember, whenever we are having the question on this deuterium exchange, you have to consider D2O. Instead of water molecule, you have to use D2O molecule. Now, what is it exactly? Look at this. When compound with acidic hydrogen atom are placed in D2O, the acidic hydrogen exchange with deuterium. What it meaning that when we have any kind of acidic hydrogen, definitely that acidic hydrogen is liable to change the proton from the compound and that get replaced by the deuterium. For example, what do you mean by acidic proton? When we call it as acidic proton, look at this example, C6H5OH, it is the phenol, well known to you. When we have the ionization of phenol, you will get C6H5O minus plus H plus. So whatever we obtain this H plus, this indicates that phenol are in acidic nature. Phenol are in acidic nature. Means phenol is in acidic nature. When we put a drop of S2O, a drop of D2O molecule instead of S2O, when a drop of D2O molecule is placed, definitely whatever we are having this OH proton means hydrogen, that is definitely replaced by the deuterium. How it is replaced and when it is replaced, that part we continue to the next slide. If you look at the further part of this presentation, that a drop of acid catalyst or base catalyst is required, but frequently the exchange occurs spontaneously. It means that we do not require a lot of D2O molecule. We require only a drop. When we are having 1 liter of the solution or 1 liter quantity of the particular solution is there, just I have to use 1 to 2 drop of D2O so that I can get the very good change. So it is very important to have that D2O in a very small quantity. It doesn't require very high quantity or larger quantity. The catalyst allows a faster approach to the equilibrium, a process that can require anywhere from the several minutes to the hours or more. It means that when we are having the catalytic reaction, some reactions are carried out very fastly, some reactions are carried out very slowly, some reactions are carried out mediumly, depending upon the type of catalyst, activity of the catalyst. What actually catalyst does? It is giving the equilibrium to convert starting material into the product. So that is the things regarding this catalyst. You know that when we have acid, it is COH group. When we are having phenols, we have the C6H5OH. When we have the alcohols, C2H5OH, or you can say ROH. And when you are having the amines, that time you have to have this RNS2. Why I am telling this group? Because these groups are the functional group which are responsible for exchanging the proton by deuterium. So remember here, whenever you will have the question, what kind of groups or which are the group that can be readily exchange the proton by the deuterium. In that case, you have to explain acid, phenol, alcohol, and amines. These are the four major groups which can readily exchange the proton by the deuterium. Other type of protons are there, but they are not much readily exchange their proton by the deuterium. So remember once again, acid, phenols, alcohols, and amines, which containing COH group, OH group, OH group, and NH2 group. Now see here, this statement is very important statement. I am using this statement as like this. I am using this statement like this. Basic catalysis work best for acid and phenols, while acidic catalyst is most effective for alcohols and amine. What it indicates? Now see here, as already we know that acid and phenols. So phenols are acidic in nature, and you know that acid acidic in nature. And when we are having the reaction between base and acid, definitely it will give neutral product. So when we are having the acid base catalyst, definitely that reaction is very fast. As phenol is in acidic, so again you will have phenol plus base, you are getting the neutral. Similar fashion, when we are having the acidic catalyst, you know that type of catalyst is acid. So definitely the OH group which containing the basic nature or alcoholic nature, that can be more effective in the exchange of deuterium to that particular proton. So remember, base catalysis work best for acid and phenols, while acid catalyst is best for alcohol and amines. So this is very interesting. You know that the concept as well. When we move to the next slide, look at this. When we are having the basic catalyst, what actually happened in that one. So this is very interesting example, RCOH. We can take any kind of acid, just like acetic acid, propionic acid, butyanic acid. So just you replace R group by any alkyl group, you will get the different kind of acids. So I have taken very simple or general reaction, that is RCOH, which is when I am putting a drop of D2O molecule. I am putting a drop of D2O molecule into it. What will happen? Look at this. Whatever I am having the hydrogen at this position, that is hydrogen of acid, that get replaced by the deuterium. When you look at the product, instead of hydrogen in the product, you observe that we have deuterium. So instead of getting RCOH, I got RCOOD. D means deuterium. And whatever D2O was there in the starting material, that was get converted into DOH. It means that one hydrogen which was with acid, that is going to attach to the deuterium, and that become a DOH. So remember here how that DOH, it is nothing but one deuterium of a D2O molecule get exchanges, or that is used for replacing hydrogen of OH of COH group, and we got RCOD and DOH. So this is this example give you more information how that base catalyst is used to replace hydrogen of COH group by the deuterium. So another example is there, phenols. ROH means it is the phenol, and you know that phenols are acidic in nature. Phenols are acidic in nature. When this acidic nature it is used for D2O. Now you will have the question. I am talking about the basic catalyst. What is meaning? I have not put any catalyst on this arrow mark. I have not written any catalyst on this arrow mark, but only I am saying that it is base catalyst. Remember here, student, it is very simple phenomena that you know that nature of water. If I ask whether water is acidic or basic or neutral, that time you can have acid is having dual nature. it may act as a acid, it may act as a base. So it having the dual nature. It having the dual nature. Yes, when water got the basic medium, definitely it act as a acid. When water got the base acidic medium, definitely it act as a base. Now see here, the starting compound which I have taken here is the acid. So therefore, this is the acid and this is the base. So in this case, D2O act as a base and this is the acid. So acid-base reaction, you got here, this is the neutral and this is the water. That is deuterated water. One can say it is the deuterated water. So this is regarding this acid and D2O as a base. Here also ROH means phenols. It is in basic in acidic in nature. So when D2O is added, which is in basic nature, so acid-base reaction, definitely will get the product which is neutral and deuterated water. So hydrogen of OH group, that is replaced by D2O deuterium, and the product form is AROD. And the hydrogen, the hydrogen which was released from the phenols that get attached to the deuterated water and that become a DOH. So this is about this basic catalyst. This is about basic catalyst. When I talk about acidic catalyst, it means that in the first two examples, what we have observed, D2OH are acting as a base catalyst. Now in the acidic catalyst, so definitely D2O will act as a D2OH act as a acid. So ROH, you know that it is alcohol. When D2O is there, it means that it is acidic and you will get exchange of hydrogen of alcohol by deuterium and you will get ROD. So ROD, and here also you get DOH, means one deuterium is replaced by hydrogen and due to that one you got DOH, means deuterated water. Now if you look at the another case, it is the amine. RNS2, you can take any kind of amine, definitely you will get the reaction between D2O and RNS2. Again, I am focusing once again here, D2O whatever we are using in the form of base catalyst or in the form of acid catalyst, it required very small quantity or a drop of D2O is sufficient to exchange proton by the deuterium from acid or base type of compound. So here RNS2 that get exchange by the deuterium that become RND2 and you will get DOH. I think here is a mistake from my side. I have to write only one deuterium. I have written here two deuterium. It is not possible. I missed to write the hydrogen here. So I have to write one hydrogen RNHD instead of two, because only one deuterium is replaced by the only one hydrogen of RNH2 is replaced by the one deuterium. So I have to write RNHD. I have to remove this deuterium and this is okay now. DOH is okay. So what I mean to say is that deuterated water at one time, or first example, you observe that it acts as a base catalyst, and in second example, you find that it is act as a acid. So therefore, we can get the exchange of proton from alcohol, amine, acid, or phenols, and that get replaced by the deuterated water, that is D2O. When we move to the next part, you will find that it is quite interesting to check the benefit of deuterated exchange or deuterium exchange. How it is useful in NMR spectroscopy, as far as NMR spectroscopy is concerned. Now see here, the deuterium exchange peaks due to the exchange hydrogen disappear from H1 NMR spectrum. Since all of the hydrogen ends up in HOD, means deuterated water molecules, the lost hydrogen generate a new peak, that of hydrogen in HOD, the NMR spectrum of particular substance is complicated by the presence of OH or NH proton. It is possible to simplify the spectrum by removing the peak arising from exchangeable proton. It is possible simply adding a few drops of deuterium oxide called as D2O to the NMR tube containing the solution of the compound under observation or under study. What I mean to say is that, look at this. When any compound do not have a deuterium, and when NMR spectra is taken, you are getting very complicated spectra. How is complicated? Suppose if I ask how many peaks are there, you may observe my photographs and you can see there are 4 peaks. You can identify this 4 peak very well because you are observing that peak very well. But when I am having this kind of peak, it means that I do not know how many peaks are there. And these peaks are complicated. They are overlapping with each other. It means that when such a kind of peaks are there, definitely what will happen there, it is not identified very easily. It become complicated. It become complicated. Means suppose I am having a 4 hydrogen over here and I got this kind of peak, which is complicated. But when I am putting drop of D2O molecule, deuterated water molecule, what will happen? 1 or 2 hydrogen from that original solution which are under study, means 2 proton get replaced. 2 proton get replaced, and instead of having 2 proton over there, 2 deuterium atoms are there. 2 deuterium atoms are there. It means that the original compound have only 2 proton. Original compound have a 2 proton. It means that instead of getting this kind of peak, I will get this kind of peak. Means peak will be observed very well. Signal will be disappear because proton will give the signal, deuterium will not give the signals. What is the reason? Because when we consider the spin quantum number or spin of proton, it is 1/2. And when we consider the spin of deuterium, it is 1. And when 1 is there, it is showing very, very big peak or no peak. But when spin is 1/2, definitely you are getting very strong peak. So this is the reason when deuterium is added into the particular compound, the complex spectra becomes simplified. So this is very important and useful information that we are getting from the exchangeable proton, or exchangeable proton means it is a deuterated proton. Now, if you look at this further part, recapping and shaking the tube vigorously for a few seconds, turn the sample tube to the probe and acquire a new spectrum. Added deuterium oxide is immiscible with many NMR solvent like CdCl3. The form a layer on the top of the solution. The presence of this layer, however, does not usually interfere the determination of the spectrum. The resonance from the exchangeable proton will either disappear or greatly diminish intensity, and a new peak owing to the presence of HOD will likely to be observed, generally between 4.5 to 5.0 ppm. What this information tells us, look at this. Whenever I am having a spectra of ethanol, suppose I want to take the spectra of ethanol, C2CH3 CH2OH, this compound, and when I have to check the deuterated exchange part of that ethanol, so what I have to do, I will take a sample tube which containing 1 to 2 ml of the solution, and when I have to take that deuterium, I have just insert capillary and put this capillary into the sample tube. In capillary, I am getting very small amount of D2O, and I am going to add that D2O into the sample tube. Just I am shaking the sample tube by capping, means by holding the hand on the thumb on the tube or having the cap over it. I am shaking it very vigorously for a few seconds. What will happen? I will get the mixing of deuterium in the ethanol. When I am mixing it very well, actually it is immiscible. It is the immiscible part. But when I am shaking vigorously with that one ethanol, definitely I can get exchange of hydrogen by that deuterium. And the layer which are coming upward or topmost layer that mix that deuterium with the ethanols, and I have to take that part for the analysis purpose. Now what happened in that case? Whatever I got the peak of OH group, it was very broad when I had the peak of compound containing CH3 CH2 OH. But when I have taken that compound into the form of CH3 CH2 OD instead of OH, it become OD. I am getting that peak. No doubt I am getting back that peak. Instead of getting very broad peak, I am getting very small peak, or sometime it will be disappear, or whatever intensity of peak is there, that will be going to be down, or that will be going to be reduced or diminished or vanishes. So that is the miracle when we are going to add G2O into that particular organic compound. So this is very interesting to understand the concept of G2O in the NMR, or application of G2O in the NMR. An interesting spectral simplification resulting from D2O exchange is observed in the case of 2-chloroethanol, which is I have given below. Means next you are getting that picture. 2-chloroethanols. So you are ready to write the structure of 2-chloroethanol. So look at this. Just 10 minutes are remaining. We will join once again. आपण पुन्हा एकदा जॉईन होणार आहे. टाइम संपला तरी, कारण आपण ड्युटीवर एक्सचेंज आज संपवणार आहे. इट इज व्हेरी इंटरेस्टिंग. The bottom NMR spectrum of 2-chloroethanol clearly shows that OH proton has a broad unsymmetric resonance centered at 2.22 ppm, and the complicated appearance of the resonance for the methylene proton at 3.68 and 3.87 ppm, resulting from fissional coupling. You know that fissional coupling, geminal coupling. Fissional coupling means hydrogen C hydrogen. Fissional coupling is also called as 4-bond coupling of hydroxy group to the adjacent methylene group, that is OH CH2 CH2 Cl. Now this is the example, or this is the structure of 2-chloroethanol. So look at this. Ethanol is the main part. So if I start numbering from here, 1, 2, at second position there is a chlorine, therefore it is called as 2-chloroethanol. When we have this kind of 2-chloroethanol, what will be the situation over here? When I am going to add D2O into this one, what will happen? Generally proton which are attached to the carbon, look at this carbon, that proton will not be exchanged. Remember here, even though compound containing the proton, but the proton which are attached directly to the carbon will not be exchanged. Only the proton which are attached to the oxygen, nitrogen, they can be exchanged. Otherwise, proton will not be exchanged by the deuterium. After adding a drop of G2O to the sample and thorough mixing, the NMR spectrum was required against. We have to take that spectra. Now see here, note carefully that when we are going to add D2O into it, what will happen over here? So nearly complete disappearance of OH resonance, means whatever I got peak of OH resonance or OH for this compound. So 2-chloroethanol is there, and this 2-chloroethanol, when I am taking the spectra of this one, I am getting the peak of OH group. But when I am going to add D2O into it, what will happen? The peak which are observed due to the OH group, that will not be observed. That will be going to disappear. So this is the main reason when we are going to add D2O into that one. So which is reduced to very weak, or if it is disappear, or suppose you obtain the peak, it will be very, very small, or will not be peak, or it is very peak. So broad signal at 2.38 ppm, the coupling of the hydroxyl proton to the adjacent methylene is removed. What do you mean by coupling? It means that, look at this. Whenever I am having this CH2 group, when proton was there, and we are taking this very pure solvent. When proton is there, this carbon having the two protons. Now this two proton is going to interact towards this hydroxy proton, and they having the interaction. So the two proton having the interaction, and when this is replaced by deuterium, this kind of interaction is going to vanishes, or it will be removed. So the two methylene groups, two methylene, this is the first CH3, this is the another CH2. So two methylene group disappear as a nearly first order multiplet. So what we are having, this first order multiplet is going to appear. Now see here actual things that I have mentioned here. So when we have the spectra of 2-chloroethanol, OH, CH2, CH2, Cl, after treatment with D2O, it means that actually this is OD, CH2, CH2, Cl, which is called as deuterated 2-chloroethanol. So this is the spectra actually I am getting there, and I got this one. Now see here, if you look at this one, this will show triplet and this will show quintet. This will show triplet and this will show, yes, quartet. How it is getting? Look at this. Now this peak is very when we are adding D2O. But if you compare that, instead of adding that D2O, if we have only OH group, what kind of things will be observed? Now see here this spectra. Now if you look at this one, in this case, we don't have any D2O exchange here. Means whatever I was having this 2-chloroethanol, and I have taken the NMR spectra of this one. So I got this kind of peak. It means that I am getting here, this is the complex spectra. Now this is the complex spectra. You know that when we have this one, I got this complex spectra. But when I am having that addition of deuterium, what will happen? This complex spectra vanishes and it will gives this kind of peaks. So look at this. You got only one peak in the when deuterium is added, but when deuterium was not there, I am not getting a single peak. I am having a number of peak or complex peak. It means that when deuterium is going to add, the complex spectra becomes simplified, and we got very clear picture, and from that we can identify the things as well. When we consider 2.38 ppm, furthermore the coupling of the hydroxyl proton to the adjacent methylene is removed, and the two methylene groups appear as a nearly first order spectra or multiplet. What it indicates? Look at this. Whatever we are having this structure, this OH, CH2, CH2, definitely when deuterium is not added, this OH group also give the singlet. OH group also give the singlet, and this OH group give the singlet. And what happen when deuterium is going to add, that singlet is going to be missed, or that singlet going to be removed very well. You can see this. I will show you very well explanation. Look at this once again. This picture, you can observe this one. Now look at this 2.2 ppm. Look at this. This is 2.2 ppm. When we are having this value and appearing this OH group 2.2 ppm. Look at this at 2.2 ppm. So when it is there, when D2O was not there. D2O was not there. But when we added D2O, this OH group get replaced by OD. And when OD is there, you will not get this spectra. You will not get this spectra. Just you look at the above. You will not get spectra at this position. Look at this. So you will not get the spectra at the 2.2 position. So this is the main reason why D2O is useful in the NMR spectra, so that the things you can understand. So the peak which was obtained in the 2.2 ppm value in absence of D2O, But when we added due to the peak which was there in the absence of due to, but it get now removed. Here peak is not removed in presence of D2O. So that kind of information you have to keep in mind. So whatever we are having these three, it is no doubt this is showing the triplet as it is showing very well that things, and it is very good. It means that here we have the OH group, but when deuterium is there, OH or hydroxy peak will not be appear. It will get vanishes. So that things already we have considered. Now see here, I will explain this again once again very well. So whatever we are having there 2.38 ppm value, the coupling of hydroxy proton to the adjacent methylene is removed and the two methyl groups appears as a near first order multiplet. Now see students, now this is a very simple example that I have taken 2-chloroethanol. So this 2-chloroethanol, how many different type of protons are there? So underline indicate the different type of proton. So this is A type, this is B type, and this is C type. In all total, 3 type of protons are there when we have 2-chloroethanol. And if you look at this, whatever I have this hydrogen in the first compound, that was replaced by deuterium. It means that when I have added that deuterated water, a drop of deuterated water into the 2-chloroethanol, I obtain here deuterated